So good evening everybody. The science of Santa. I have in the past given talks about how the moon landings were hoaxed, and I've given talks about UFOs. And in some cases, the following day, I've received vitriolic emails telling me how I was completely wrong. In this case, I'm hoping not to get a whole load of emails from 7-year-olds telling me how I've got the science of Santa all wrong. So the basic question is Santa compatible with the laws of physics? Or to redirect it slightly, how many laws of physics does Santa break? We're going to sort of top them all up, and then we're going to come to a conclusion at the end. So I'm sure you all know, but we'll state the claim anyway. So Santa is allegedly a portly, jolly fellow with a white beard and a penchant for wearing red suits. Now, although that does display a certain amount of questionable fashion sense, that doesn't actually tell you anything about whether he exists or not. So what about the claims that are made regarding his rather incredible feats? In other words, the claim that a Santa visits all households on Christmas Eve to deliver presents to all qualifying children. And what do we mean by qualifying? Well, of course, Santa has his naughty and nice list to define which ones should get a present and which ones shouldn't. Can we reconcile these feats with our understanding of science? And in particular, the science that we're going to draw on, I decided to actually draw on the science described in my other talks. So in other words, I looked back at some of the talks I've given over the last year or two and asked myself, is there anything in those talks that helps us answer the question as to whether or not the feats of Santa, the alleged feats of Santa, actually are compatible with the laws of physics as we understand them? Now, we actually know that Santa is a fan of science, because if we think about, for instance, the periodic table there with all the elements, we know where all of these elements come from. We know that hydrogen and helium were made in the Big Bang, and all of these other elements were made inside stars, small stars, large stars, or possibly supernova. That was all dealt with in, as you can see in the bottom left there, the ABC of stellar evolution told us where all these elements come from. But we can tell that Santa must be a fan because, of course, his mantra is always referring to his favourite element, element 67, which I'm sure you all know, yes? Yeah, because you're all very familiar with the periodic table, and so you know what element 67 is. Of course, it's a rare earth element, and his favourite is, of course, holmium. There it is down in the rare earth section of the periodic table, if you didn't already know that. So that gives you a sort of level of the calibration of the humour. If this was a real live audience, I would be able to tell whether you found that funny or not, and I would then adjust the rest of my talk accordingly by jumping over those slides, which I think would go down and bomb. But let's get to the grips of what it is we're talking about. We're going to examine that statement there, that Santa visits households on Christmas Eve to deliver presents to children. We're going to take that sentence and pick it to pieces and see if any of that violates what we understand according to the laws of physics. So let's start not with the first word, how many children Santa is giving presents to. So we can just do a very rough back of the envelope calculation. None of what I'm going to show you is accurate. It's just orders of magnitude, roughly how many children are there in the world? How many children get presents? Well, the Earth's population is about 8 billion. Roughly 1/4 of them are children, and roughly 50% of the world would be recognised as either being Christian households or not being strongly aligned to any other religion, which would stop the children receiving gifts from Santa. Now, that's probably an overestimate, but we can say that for the sake of argument, about 1 billion children are eligible for Christmas presents. And again, the asterisk there reminds us that we need to think about the naughty nice list. So let's just assume no one's on the naughty list and everybody's on the nice list. Yes, it's true that some children stop believing in Santa after a given age, but Santa doesn't stop believing in children, and just in case, he has to be prepared to deliver presents to all of them, just in case they all, in a given year, decide they do believe in him. So let's just take a billion. Other people have estimated somewhat smaller numbers. Let's just stick with 1 billion just because it's a nice round number. So Santa delivers presents to a billion children. Okay, now Santa apparently visits lots of these households containing children. How does he actually visit? How does he get around? What's his basic mode of transport? Well, we know what his mode of transport is. It's a sleigh pulled by flying reindeer. So one question we can ask is, can reindeer fly? Okay, we know that insects fly, we know that birds fly, we know that pterosaurs fly. Pterosaurs are pteranodons and pterodactyls. You don't tend to see many of them around these days, but they fly as well. And of course, even some mammals fly. So there's plenty of examples in the animal kingdom of flight. What about reindeer? Well, if reindeer can fly, then they apparently choose not to do so for quite a lot of the time. There's very little evidence out there. No matter how many YouTube videos you look at, you very rarely find anything that shows you flying reindeer. But we have to remember that we're taking a scientific approach to this, and we must remember the adage, absence of evidence is not evidence of absence. So just because we look at YouTube and can't find videos of flying reindeer does not mean that reindeer cannot fly. So in other words, we have neither proof nor disproof of flying reindeer. We just have to leave that one as undecided. The jury is still out on that one. Okay. But if you work out that Santa is flying around the world, if he wants to visit 1 billion children in about 36 hours, I'm using that number again just roughly, in the Northern Hemisphere the nights are a bit longer than 12 hours, in the Southern Hemisphere they're a bit shorter. If Santa is careful about how he delivers in his regimen, then he can use the fact that there are 24 time zones around the world, so he can use the spin of the Earth and he can use the 12-hour on average nights. It gives him about 36 hours. But if he wants to visit 1 billion children in 36 hours, he would have to travel at a minimum of about 2,000 kilometers per second, or 0.007 of the speed of light. But of course that's tiny, less than 1% of the speed of light. Even if we decided to allow Santa a little bit longer at each venue, at each household to visit, then even if we doubled that or tripled it or quadrupled it, the speed at which Santa moved would still be much less than the speed of light, and so Santa would not be in any danger of defying the laws of physics that state no object can travel through space faster than light can travel in a vacuum. Yes, we know that space can actually expand faster than light. We heard about that in the beginning of everything, at the origin of the universe, and we heard about it when talking about quasars in the very remote parts of the universe as well. But the fact that space can expand at more than the speed of light, that's different. We're talking about objects moving through space where you have quite definitely a limit of the speed of light. But we're nowhere near that limit, so everything is fine so far. But surely, if you move fast through the air, wouldn't the sleigh burn up? Wouldn't we have roast reindeer? Well, just as for a meteor or an asteroid entering the Earth's atmosphere, the air in front of the sleigh would be compressed and heat up. Sometimes it's mislabeled as air resistance or friction. Strictly speaking, when an object moves quickly through the air, it's not air resistance that makes it heat up, it's the fact that it's compressing the air in front of it. And we know that what happens when you compress things is that they heat up. We learnt about that in the ABC of stellar evolution. The C of the ABC stands for compression produces heat. In other words, when gravity compresses a star, the star heats up, the temperature goes up, and ultimately thermonuclear fusion starts and the star then ignites. So we know that if you're going to be moving really fast through the air, if we want Santa to visit so many places in one night, then surely we're going to have compression of the air producing heat. Now, yes, you might think about redesigning the sleigh. The traditional design isn't so good for moving through the air particularly fast. Maybe you need something more aerodynamic, but even that would suffer the same problem, compressing the air and heating up. So wouldn't the sleigh be glowing really, really white hot? Compression produces heat, we've just said. Hot objects radiate light, so surely the sleigh ought to be easily visible in the sky. Well, maybe it was. It was a little bit premature, perhaps, for Santa to be bombing around a few years BC. The idea of delivering Christmas presents before Christ was born doesn't seem to really work. Maybe, I don't know, maybe he was doing some market research. Maybe he was doing a dry run because he figured that sooner or later it wouldn't be that many years before all of the kids in the world will be asking for Christmas presents. So he was just checking out how long it actually took to go around the world a few times to see if it was feasible or not. And if you don't believe that the sleigh was actually visible 2,000 years ago, then maybe you're more likely to believe it's visible now. There's always the possibility that it has been sighted at various times in the more recent past. Maybe. But coming back to this idea that surely if it's moving really fast, it'll compress the air will heat up, and surely the sleigh will glow white hot. We can ask ourselves, well, what do we actually know about that does not emit or reflect light, or indeed any other type of electromagnetic waves? And of course the answer to that is dark matter, yes. So if Santa and his sleigh are made of dark matter, then even if it got hot, dark matter does not emit light, it does not reflect light, it does not absorb light. So you would never see the sleigh as a white hot dot of light going across the sky on Christmas Eve. Not only would it not glow and emit light, but also because dark matter doesn't absorb any electromagnetic radiation, that means it wouldn't absorb radio waves either, or reflect radio waves. In other words, the sleigh would not show up on radar. So there we go, 2 birds with 1 stone. If the sleigh is made of dark matter, it won't be visible by eye and it won't show up on radar. Surely, if we've got 2 birds with 1 stone, that must be the explanation. Okay, we'll park that one and think about other possibilities. Let's come back and examine the alleged feats one more time. We've thought about 1 billion children, and we've thought about Santa visiting by zooming around the world. What about the fact that he has to visit each household to deliver the presents? How is he going to get down the chimney? How could Santa possibly get down so many chimneys? If he wanted to visit 1 billion children in one night, he would have to squeeze down something of order 3,000 chimneys each second. Part of that is based on calculating how long it takes him to get from A to B, and we have to assume that these billion children are in households which are distributed across the world. I know some of them are actually concentrated in cities, etc. Let's not worry about that. Ballpark figure, he has to squeeze down 3,000 chimneys each second. Now, remember, Santa is a rather portly gentleman, apparently, allegedly, and therefore he would have some difficulty going down chimneys. There isn't enough goose fat in the world to make him slide down nice and fast. So what are the alternatives? Well, there are other ways of getting down a chimney really fast. And one is to rely on our understanding of quantum mechanics. And the talk here, The Weird World of the Very, Very Small, is talking about how quantum mechanics goes completely against our notion of common sense. We know that atoms are made of a nucleus with a load of electrons buzzing around them in that sort of graphic that you can see on the splash screen there. And we know atoms tend to be a particular size in the sense that when you put atoms together into molecules, into materials, they tend to have a certain size and they tend to want to be a certain distance between them. But if you were to take all the electrons and swap them out with a different elementary particle, a so-called muon, a muon is a little bit like a heavy version of the electron. So if you take all of your atoms and you keep them all where they are, but then you swap all the electrons for muons, the muons are heavier, and as a consequence of that, all the atoms would then be a lot smaller. The atoms would actually be something of order 200 times smaller. So if Santa was able to manipulate the particles in his body and swap electrons for muons, instead of being somewhere about 1.5 to 2 meters, I'm not sure exactly how tall he is, but instead of being of order a couple of meters high, he would end up being about a centimeter or so high. Which means he would fit down the chimney, no problem whatsoever. Simples. Okay, so all he has to do is shuffle some of his elementary particles inside the atoms that he's made of, and he would be able to go down the chimneys, absolutely no problem whatsoever. But of course, that only solves part of the problem because not all houses have chimneys. How could Santa get inside a house or an apartment that doesn't have a chimney? Well, we have to find an alternative that doesn't involve shrinking Santa down. But again, quantum mechanics comes to our rescue a second time, because an object like Santa could in principle move through a wall or a door by quantum mechanical tunneling. Tunneling is phenomena that doesn't exist in classical mechanics. Isaac Newton wouldn't understand what we were talking about if we talked about tunneling, but quantum mechanics tells us that when we're dealing with particles, an electron or an atom or even larger objects, it is possible for that to simply pass through a solid object, and it's possible for one solid object to pass through another. It's not very likely, but it can happen. Maybe Santa has found a way to actually increase the probability of that occurring. We know that tunneling is not just a fanciful theory. We know it actually happens because it explains, for instance, radioactive materials. It also explains how we can build a microscope based on that principle. We can build a so-called tunneling microscope that relies on that principle, that particles can actually move through where they shouldn't be allowed. They can move through a barrier that Isaac Newton says this should not happen, but quantum mechanics says, well, actually it can happen. This phenomena does allow us to build microscopes that actually then can observe individual atoms. So we know tunneling is not just a theory, we know it explains a number of different phenomena. Maybe Santa has figured out a way of getting the probability up a little bit so that it not only works on a small scale, but works on a somewhat macroscopic scale as well. Okay, we've talked about visiting and households as well as a billion children. What about the fact that all of this happens on Christmas Eve? Okay, all in one night. How can Santa make so many deliveries all in one night? If he's even travelling at relativistic speeds, a fair fraction of the speed of light, how can he possibly do everything in 36 hours? Isn't that a big ask? Well, quantum mechanics to the rescue a third time. We know that subatomic particles can be in two places at once. So in that case, why can't Santa? I've said subatomic particles, implying that, well, that works for electrons, but pretty much nothing else. Well, actually, it's been verified that an electron can be in two places at once. It's been verified that a nucleus of an atom can be in two places at once. And it's been verified that if you put atoms together in a molecule, then the molecule can be in two places at once. And some molecules are actually huge compared to individual atoms. This phenomena that a particle can be in two places at once has actually been verified for particles up to the size of a virus, which at the moment we think is a rather small entity, but of course on an atomic scale a virus is actually huge. It's made up of thousands upon thousands upon thousands of atoms, and that behaves in the same way. A virus particle can be over here and over there at the same time. This is another example of quantum mechanics telling us things that don't make sense at all when we try and apply common sense, but quantum mechanics appears to be correct. If quantum mechanics tells us something that is at odds with common sense, it's common sense that's wrong. Quantum mechanics appears to be right. So it is possible for Santa to be in two places at once. If it works for electrons and it works for a virus, why can't it work for things larger than a virus? Why can't it work for a macroscopic entity such as a man in a red suit? Even if you don't like that, even if you say, no, I'm not happy with that idea of Santa being in more than one place at the time, making it easier for him to deliver lots of presents over the world in 36 hours. Well, even if you don't like the Santa can be in two places at once, we still have alternative ways of him making the deliveries. We can say, okay, the shortest distance between 2 points is a straight line. Well, not strictly speaking, not if you change the way space and time behave. And we know that the existence of matter changes space and changes time. We saw that in the talk, Warping Space and Time. It's at its most extreme for a large, massive object such as a black hole. it would be true, well, okay, Santa is a portly gentleman, but he's not that massive. But if he was capable of distorting or warping space and time in much the same way that ordinary matter or dark matter can distort space and time, maybe he's found a way of doing that such that the shortest distance between 2 points is no longer a straight line. Maybe you can now take shortcuts in space or shortcuts in time to get from A to B as quickly as possible. So, that in principle is possible. We know that space and time are distorted by matter. Santa is made of matter, and if Santa uses some additional matter, he might be able to distort space and time in the way that's necessary to allow him to make those deliveries. So we think about how he gets around, we thought about households, and we thought about the timing. What about the fact that as well as doing all of this, he's got to deliver presents to all of these children? So what are we talking about? How could Santa carry everything he needs? If we have one present for each of 1 billion children, okay, perhaps an overestimate, but how could the sleigh hold a fraction of a billion presents if we're talking about a reasonable fraction of a billion children all getting one present each? That's an awful lot of PlayStations. So what are the possibilities for how he could possibly deal with that? Well, there are, again, a number of options that he could employ. One of them is to warp space in such a way that the sleigh is bigger on the inside than it is on the outside. So we're coming back to general relativity again. Isn't that really useful? General relativity gives us a solution. You just change the way space is configured, you warp space such that the sleigh is bigger on the inside than the outside. Some of you might think that is science fiction because you know about Doctor Who and the TARDIS, but actually black holes are bigger on the inside than they are on the outside. So if it works for a black hole, again, why shouldn't you be able to distort, warp space in such a way that the sleigh, although it appears to be only a given size on the outside, is actually much bigger on the inside? That's one solution. An alternative, again, if you don't like that answer, an alternative is to say, well, why don't you just store the presents somewhere else? Why don't you store all the presents in another dimension? We know of 3 spatial dimensions, 1 of time and 3 of space. So the 3 spatial dimensions are effectively left, right, forward, backward, and up and down. Those are the only 3 that we are aware of. Those are the only 3 dimensions that we can sense. But there may be a lot more. There are plenty of theories, especially string theories which talk about the way the universe is put together, and they assume that we don't have just 3 dimensions of space. They assume that we have 9 or 10 or 26 dimensions of space. That sounds like a lot, yeah, it sounds a bit crazy, but this is what people who are trying to understand the universe are trying to put together, theories in which they explain the way the universe is constructed. And some of them require that the universe has more than 3 dimensions of space. Now, some of them are difficult for us to access because we can only see the 3 that make sense to us. But if those other dimensions are there, well, maybe Santa has figured out a way of accessing them. So all he has to do is take the presents as made by the elves or whatever, put them in another dimension, go visiting the various households, and when he visits each household he just pulls them out of those other dimensions and puts them under the tree. Simples. Now if those dimensions don't exist, then maybe that's not a very sensible explanation, but if those dimensions are there and it's simply difficult for us to see them, maybe Santa has figured out a way of accessing those dimensions. Okay, yes, maybe, but wouldn't all of that need a huge amount of energy? Talking about Santa going at ridiculously high speeds and moving 1 billion presents around for all of these children, wouldn't that, one way or another, either moving really fast or distorting space or time, so that it allows Santa to make these deliveries? Whatever the solution is, surely that would need a huge amount of energy. Well, yes, it would. And yes, general relativity again. We've already seen in warping space and time that a black hole could power a starship. And if it can power a starship, why can't it power a little sled, a little sleigh, zooming around the Earth in 36 hours? No problem whatsoever. The Hawking radiation from a black hole could easily give you all the power you need. But alternatively, there's an energy source that we've all been overlooking. What is the elephant in the room? What's the energy source that we're forgetting? That's right. What happens to all the mince pies? Now, Santa, okay, they're not all mince pies because different cultures have different ways of feeding Santa. Some leave mince pies, some might leave cookies or other things. Let's ignore the differences and assume that calorifically they're all essentially the same. The content of a mince pie is subtly different from the contents of a cookie, but not enough to cause us any problems with the laws of physics. It is ridiculous to think that Santa eats all those mince pies. There are millions, if not billions, of visits that he has to make, and if some of them leave a mince pie, it's crazy to think that Santa would eat those mince pies. What if instead of eating them, he took all of those mince pies and extracted the energy inside those mince pies? What if Santa has found a way of converting all the mass of a mince pie into energy? E equals mc squared. How much energy would that give? How much energy would then be available to Santa to use? Let's have a look at some numbers. If you don't like numbers, look away now. One mince pie, E equals mc squared, where m is the mass of a mince pie, and most mince pies are about 50 grams or so, roughly speaking 50 grams. So if we put 50 grams in for the mass and multiply by the speed of light squared, we get an answer for the energy, 5 times 10 to the 15 joules. Now, I'm sure you don't like the unit of energy that I'm using here, joules, so just think of it as, it's sort of like a calorie. It's a little bit smaller than a calorie, and I'm going to stick to the standard unit of energy. I'm not going to convert them into calories. So one mince pie, if you could take the matter and convert it to energy, would give you 5 times 10 to the 15 joules. If a few % of households leave a mince pie for Santa, some won't bother. Some might get eaten by Santa, but only a very small fraction. If a few % leave a mince pie and Santa uses the mass in those mince pies, that could be as many as 20 million mince pies that he has at his disposal. 20 million multiplied by the number we've just calculated gives us a total of 10 to the power 23 joules. Now, I'm sure you have no way of visualizing what 10 to the power 23 joules actually amounts to. So let me tell you this. If we took all of the energy that's coming out of Sizewell B nuclear power station, not in a day, not in a week, not in a month, but if we took the sum total of all the energy coming out of a nuclear power station, added up over 1 million years, that would be roughly the amount of energy we're talking about. If Santa can convert mince pies into energy, he has an absolutely humongous amount of energy to play with, and then it's possible for him to either go very fast or start distorting space if he wants to. How do you extract E equals mc squared from a mince pie? Well, I'm not sure how. One option is to take a mince pie, and what would you do with that? Well, I guess you collide it with an anti-mince pie, and you collide them together in the Large Mince Pie Collider at CERN, perhaps. Now, that's one way, that's a very efficient way of getting all the energy out of a mince pie, but unfortunately it does beg the question, yeah, but where do you get the anti-mince pies from? That's for sure. Yeah, okay. There must be an alternative, and there is another way to extract not all, but at least a large fraction of E equals mc squared from a mince pie. What I'm about to say does not work 100%. You might be able to get a third of the energy, a quarter of the energy compared to a mince pie collider. But if you simply take the mince pie and drop it into a black hole, that's actually a very efficient way, a very efficient way of converting matter into energy. We know that is the case because, for instance, when I talked about ancient light, I talked about imaging a quasar, and a quasar at its heart is a black hole into which a lot of matter is falling. Okay, the matter is probably not mince pies. The matter is probably hydrogen, helium, maybe a few stars are falling into the into the black hole, but the heart of a quasar generates enough energy from all of this infalling matter such that a quasar can be imaged, the one I was talking about in Ancient Light. I obtained an image of that quasar, even though that quasar is at a distance of 25 billion light years. That image was obtained even without a telescope. That tells you that there is an enormous amount of energy pouring out of that quasar. So we know that matter falling into a black hole can produce huge amounts of energy. Now, okay, we know it works with hydrogen, helium and stars dropping into a black hole. How much energy can you expect to get out of a mince pie being dropped into a black hole? Well, shockingly, I can't find out. I have researched this, I've Googled it, I've looked on YouTube, but I can't find any research papers on the topic of how much energy do you get out when you drop a mince pie into a black hole. It's as if nobody is working in this particular research area. Shockingly, I don't understand why, but there you go. The field is completely wide open if anybody wants to give it a crack, by the way. So how can Santa actually do that? It's all very well saying these are all possible. Yes, you can in principle distort space and that will allow you to do this. In principle, you can go fast enough. If you can take the mince pies and convert the matter to energy, that will give you enough energy that you can go fast. But how could, for instance, Santa manipulate space and time? It's all very well saying it's not disallowed by the laws of physics, but how could Santa possibly manipulate space and time? Well, one thing you've got to bear in mind, nobody said Santa has to be human. Why not? Okay, doesn't look particularly portly, certainly doesn't look very jolly, but I'm sure we all agree is certainly capable of manipulating space and time. So maybe that is a possibility we should simply be aware of. Nobody seems to think Santa looks like that, but who actually knows what Santa looks like? You're not supposed to ever be able to see him. You should be asleep by the time he comes to deliver the presents. An attempt has been made to work out what Santa looks like, if you believe that Santa and Saint Nick are actually the same person. Saint Nicholas, his skull exists. If you believe that Saint Nicholas was a 4th century Greek bishop, his skull exists, and Facial Reconstruction Laboratory, a laboratory in Liverpool John Moores University, has taken his skull and used tissue depth data to facially reconstruct what Saint Nicholas would have looked like. And they've come to that conclusion. Now, okay, they've put a beard on this person because that's the convention, and maybe he does and maybe he doesn't look much like the sort of Saint Nick that we are used to. But you have to remember, of course, that facial hair and skin colour, whether it's green or not, and the shape of the ears, whether they are pointed and green, that's all conjecture. So we believe that might be the face of Santa, but of course we don't actually know. So coming back to the original question, is Santa compatible with the laws of physics? I asked the question, how many laws of physics does Santa actually break? And I think I've convinced you that the answer is none. So feel free to draw your own conclusions about the existence or otherwise of the portly, jolly fellow with a white beard and a penchant for wearing red suits. Regardless of your conclusions, may I wish you a socially distanced but still very merry Christmas. Thank you all for listening.